So recursive decomposition generally suited to problems that are solved using divide and conquer strategy. Divide and conquer. Divide and conquer. You come from higher to lower. How? We'll see next. A given problem is decomposed into a set of subproblems. These subproblems are recursively decomposed further until desired granularity is reached. How? We'll see next. Here, you can see the example of classic divide and conquer algorithm, which is quick sort. Quick sort algorithm. You already learned this algorithm in data structure. Quick sort. In quick sort, we have a list of number. Like here we have 5, 12, 11, 1, 10, 6, 8, 3, 7, 4, 9, 2. This list of number, how we sort this? First of all, we have to select the pivot value. The pivot value, any value we call pivot value. How we select pivot value? It can be small, it can be higher, but normally we take the medium value, the moderate value, not high, not low, but in between value. Okay, you will see this, that what happened if we choose high value, what happened if we choose the low value. Okay, so the thing is that we have to choose like in between value. We call median value. Median value. Okay, in this case, 1 is the lowest value. So if we choose this one, so it is simple, but it may perform poorly if the list is already sorted. Last element, we can choose the last element. It's also simple, but also lead to worst case performance in some cases. But we will choose middle element. Yes, this is better for avoiding worst case in sort. Or we can select any random value, any random. Also we can choose random, no issue. Or we can choose the median of 3 paired value. Like we choose the median among first, middle, and last. We call average. Very common rule because it produces better performance on average. We can choose the average value as well. So it depends. It's up to you. So here in this case, the value we choose is 5. For example, 5. So how we distribute this list? Left and right values. So left will be, we choose less than 5. Okay, left must be less than the pivot value, and right must be equal to and greater pivot value. So left we choose less than 5. 5 is pivot value. So 1, 3, 4, 2. And right we include 5, 12, 11, 10, 6, 8, 7, 9. Mean 5 and greater. Faham? Understand? Yes. So next step, if we see next step, okay. Next, again we choose pivot value. So here we have 4 element, 1, 3, 4, and 2. We can choose 4, we can choose 2, we can choose 1, but we want to choose mid value. Somehow 3, okay. 3 also okay. So for 3, again, left side less than 3 and right side 3 and greater than 3. So left side 2 and 1, right side 3 and 4. And if we go to other side, the list 5, 12, 11, 10, 6, 8, 7, 9. So we choose the pivot value 9. So left side, it must be less than 9, and right side, it must be 9 and greater. So we have 7. You see, you can choose 7, 8, 6, and I think 5 or 7. Yeah, 5. Understand? And other side, we have 9 and greater than 9. 9, 12, 11, and 10. Again, from left side, if we come to left side, we have only two, 1, 2. So we choose 2. It means 1 is left and 2 will be right because we have only two values. And second one, 3, 4. We choose 4. So 3 will be left, 4 will be right. Yeah, we can choose only this value. And then 5, 6, 8, 7. We choose 7. So left side 5 and 6, and right side 7, 8. And then 9, 12, 11, 10. We choose 10. So less than 10 is only 9. And 10 or greater is 10, 11, 12. And finally, last step, we can see 5 and 6. We choose 6. So 5 is left, 6 will be right. 7 and 8, we choose 8, 7, 8. Okay, same thing. And then 9 is only one single, no need. And the last is we choose 11. So 10 will be left side, 11, 12 will be on right side. First two, last, we choose 12 and 11 and 12. So you can see we already sort the value, the list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You see this? So we already sort the list. Yes. Understand? Yes. Very easy. Okay. Muhammad Fahmi. Fahmi.
Ya saya.
Fahmi Iman.
Ya saya. Hello.
Yes, Fahmi Iman.
Boleh dengar ke tak?
I can't hear you.
Alamak, mic Ron salah, aduh.
Okay, please explain.
Which one? Sir. Oh, okay.
Your voice is very low. Anyway, please explain this.
Efficacy composition.
Hurry up.
Kejap ya. Share favorite. Ni, sekejap, quick sort. Repeated recursively. I'm lost lah, sir. Hello?
Yes.
Uh, sir, boleh dengar, sir?
Yes, please. Who will explain? Who will explain? Any volunteer? Nurdini? Nurdini Shakrin. Shakrin. Yes, Nurdini. You explain? Yes. Muhammad Danish. Muhammad Danish Akmal. Yes. Who will explain? Any volunteer?
Sir.
Yes, please try. Try. Good.
Uh, so for this recursive, for quicksort, it uses what we call divide and conquer. So for the first list, it's split into two in the middle. So for so it sort first or for apa ascending, and then it is being divided in the middle. So for 1 3 1 3 4 2, and then it is divided into two. So for the left side is 1 2, and for the right side is 3 4, and it is divided again. So 1 2 3 4. So that is sorted. So for the right side, 5 6 8 7 6 9 12 11 10. It is split in the middle. So for the left side, 5 6 8 7, it is split into two, and then it is split more into two, 5 6 7 8. So for the right side, 9 12 11 10, it is split 9 10 12 11, and then split again. So we got the sorted on the last list. I think that's how it works.
Okay, good. Thank you very much. I'm Azamir. Okay, so Pastu, we have the algorithm. So in algorithm, same thing that we have to find the minimum value, like same thing, like we have to find a minimum value with nothing. If AI is less than minimum value, then it will assign to AI. And then Pastu, next is basically actual recursive minimum value. How we find? We find from left and right, left min and right min, right? LMNIN and right R MIN. And we have to see the formula for this. And then if left is less than right, then minimum is equal to L, L min, and otherwise it will be on right side. It will be on right side. Okay. Like less than the pilot value, definitely it will be left side, otherwise right side. So no need to see, I will not give any algorithm in the exam, but you should know the science behind this. The actual programming steps behind this is this algorithm. Okay. Then see, this is also like recursive decomposition. This is recursive decomposition example with quick sort here with the help of minimum value. So the code in the previous slide can decompose naturally using recursive decomposition strategy. We'll illustrate this with the following example to find minimum number in the set. For example, we have 4 9 1 7 8 11 2 12. You can see the last level, the level 3. Level 3. So what we can do, we will do minimum function with every two values, like 4 9, 1 7, 8 11, and 2 12. So the minimum of 4 9 is 4, and the minimum of 1 7 is 1. Minimum of 8 11 is 8. Minimum of 2 12 is 2. Plus 2. Minimum of 8 and 2 is simply 2. And minimum of 4 1 is 1. So we can get the minimum value, which is 1 and 2. Very simple. We have just used the minimum function. Okay, we can decompose our problem like this. This we call recursive decomposition. Very easy, very simple. Okay. Any question here? Yes, any question here? Second is data decomposition. Identify the data on which computation are performed. Partition this data across various tasks. This partition introduces a decomposition of the problem. Data can be partitioned in various ways. This critically impacts performance of parallel algorithm, like output data partition, input data partition, output and input data partition, or intermediate data partition. How it works like this. Often, each element of the output can be computed independently of others, but simply as a function of the input. A partition of output across tasks decompose the problem naturally. And this is very simple. Just we have to do the multiplication steps. We'll see, like in matrix multiplication, we can break the problem as much as we can. Like for example, here output data decomposition example. Consider the problem of multiplying 2n by n matrix. N by n mean same element matrix, 4 by 4 matrix, 5 by 5 matrix, 6 by 6 matrix, 6 row, 6 column. Matrix A and B both are same. To yield matrix C, to get matrix C, the output matrix C can be partitioned into 4 tasks. How? If we multiply 2 matrix into and got the result value in other matrix, so very simple. How we get C11? We get C11 with the A11. A is the first value or first row, first column. A11 with of the second matrix, first value, first column, B11 plus first two A21, because we have to choose here the column, and we have to choose the column of next, like A12, A12, and then multiply B21, B21. First row, first column, first row of A and first column of matrix B. And then first two, what we have to do, we will choose again same thing. We have to choose first element with the second column, yes. And then in task 3, what we'll choose? We'll choose the second column of matrix A, which is, sorry, second row actually, second row of matrix A, which is A21, and then it will multiply with the second column of matrix B, A12 plus A22 into B22. Simple, 4 steps. Very simple matrix multiplication. It's not a rocket science. Understand? We can break this task into 8, into 12 also can. Faham? Any problem? Yes, any problem? Yes. So this is week number 6, I think. So we have, this is week number 6 or 5. Anybody? Please rectify me, correct me. We are enter in week number 6 or 5. Yes. Anybody?
6. Uh,
Week number 5 or 6. Yeah, this is week number 5. Okay. This is week number 5. It means that this will be our last chapter for test 1. I will complete this chapter. I think by next week. It should be by next week. Let me see the SOW again. Okay. So week number 5, 6. Okay. So we have to linger on this chapter till week 6. Understand? But the thing is this, that let me check. Let me check with the date wise. Okay, week 1, 2, 3. No, this is week number 6. Okay. Somebody already told me that this is, thank you, week number 6. So we are in week number 6. This is not 5 week. Okay. This is week number 6. So maybe we'll see. I will inform you when will be our test 1. Normally it's week 8. So understand, this is week number 6. Please, this is not week number 5. So this is done. We are in week number 6. Okay. And secondly, I have to complete this by this week. Means that your test 1 will be from, yeah, this chapter, this complete chapters. Okay. So test will be in normally week number 8 actually. I will inform you before. Okay, so week number 6 must be till data decomposition. For example, I can, if I show you I show you. Okay, I will show you later. But I am okay. Any question here? Yes, please. Any question? Any question here? Yes. Any question? So very simple matrix multiplication. Here, same thing. A partition of output does not result in unique decomposition into tasks. For example, for the same problem in the previous slide, same problem, we with identical output distribution, we can derive the following two other decomposition. We can choose this, we can solve this problem like this into 8 step. 8 step mean we further break like C11 only first task only multiplication, and then C11 will be C11 plus A12 B21. Like we break this task into eight. Can how? First we do only A11 B11, and next step we will do the because A11 B11 in C11. Okay, so we can do another step with C11 A12 B21 like this, and then third step only A11 B12 only this, and store will result will be stored in C12, and fourth step C12 is equal to C12 plus A12 B22 like this. So we can solve this into 8 steps, 8 tasks simply, either this way, either this way, same thing. It means that we can decompose in different ways, like we can break in more subtasks. We can break in more subtasks. It depends. The purpose of this example is just that we can break the problem in more subtasks. Faham? So we can change in different way. Like here, task 3, you can see task 1 is same in decomposition 2. Task 1 is same. Task 2 is also same. But task 3, we just use only like with A12 and B22. So we can do any of the value, no issue. A12 and B22 can. And then we write here A12 like A11, B12, and then C21, A22 into B21. So it depends. We can use any of the row and column, and then we have to do addition. Simple. Yes, any question? So we can choose any of the row and any of the column. It's up to us, but it should be one time, not more than one time. Simply. Like here, task 3, C12, A12 into B22. So here, if you see, C12 is basically A22 into, sorry, here, A12 basically A12 and B22. Here, A12 and B like this. So we can multiply any of the value, but it will be in add steps, Lapan step only. But the step must be used one time, not repeat. So we can decompose it like this, and we can decompose like this. The answer will be same. The answer will be same. Understand? Yes. Any question? Any question?
No, no question, sir.
Okay, very simple thing. Okay, so here, now we'll see another way. Computational problem. Calculate the item set frequencies. Item set frequencies. Item set frequency means how much that item is repeating again. We write that frequency, that occurrence, one time, two time, three time, four time, based on the given item set in the database transaction. For example, transaction could be grocery store database of customer sale. Transaction could be individual grocery list of a shopper. Item set could be a group of items in a store. The objective is to find out how many customers, how many frequency customer each of the designated group of items. For example, here, very simple. We have database transaction A, B, C, E, G, H, like this, okay? So if you see here, so we'll see how many time A, B, C is repeating. In the second item, if you see here, item sale, this one, database, this one, if you see this one, okay, this is basically, if I, okay, here, database transactions, then we have item data, and then item frequency, item set frequency basically. So if you see, we have database transaction A, B, C, E, G, H, like this, B, D, E, F, K, L. So if you see here, item data ABC. So how many times ABC is repeating? Only one time, the first one. See, rest no ABC. So we write one. And next DE. How many times DE is repeating here? So DE in second value, and D is in third, and D is in, yeah, second last. So we write three times. Tiga kali. CFG zero kali. Kosong no. AE dua kali. CD satu kali. DK dua kali, and BCF kosong and CDK kosong. This is one of the way that we can see, like for example, this is the application they write here, that the objective is find out the group of items, the group of items basically, that how many customers bought each of the designated group item. We choose a group A, B, C, D, E, like this, and then we see that we have selected that how many customers bought each of the designated group items. Faham? Very simple thing. If we see next, input data partitioning, generally applicable if each output can be naturally computed as a function of the input. In many cases, this is the only natural decomposition because the output is not clearly known. We call a priori mean the problem of finding the minimum is in a list, sorting a given list already given. A task is associated with each input data partition. The task performs as much of the computation which is part of data. Subsequent processing combine these partial result. Same thing, database counting example, the input, that is transaction set, can be partitioned This induces a task decomposition in which each task generates partial counts of all items. These are combined subsequently for aggregate count. For example, we have task 1, we have task 2. We can see that same thing, database transactions, and then we have item sets, and then items frequency. We can see the item frequency very easily. If we have item set of A, B, C, D, E, we can check the repetition or the frequency in the database transaction. Very simple. So we can write in the item set frequency. Like ABC, how many times ABC repeating? Only one time. DE, dua kali. CEF, CFG, kosong. AE, satu kali. So same thing. It's also the same thing. Often input and output data decomposition can be combined of a higher degree concurrency. Here actually we are distributing tasks in many what we are doing here, we are actually splitting the task into many. Okay, it depends. So we can go towards like 4 tasks, 8 tasks. It's up to us, because while we are distributing tasks, because we have our resources. For example, I have 8 people, 8 students. So how I should give the balanced task to all 8 students. If I have 16 students, I have to distribute the task among 16 students. If 20 students, so I have to split or decompose the task and divide equally. Okay, try to divide equally. Sometimes it doesn't necessarily that we have to distribute a task equal. It's very difficult, but anyway, we have to justify the distribution, the load among the students. Okay, so the task among 8 processors is not like this. We use only one processor or 2 processor. No, like for example, we are working in computer science department. We are 30 faculty members, so we have to divide the workload equally. Like I am teaching 2 subjects, 3 subjects, same thing. Dr. Mansir or Dr. Wahid or Dr. Latifa, Dr. Feroz. So we have an equally load. It doesn't mean that I am working, all classes are teaching by me. No, we have equally workload according to the resources. Faham? Understand?
Paham tak?
Yes, very simple thing. Very simple thing. Yes, it depends upon the resources. We have to utilize the resource. Intermediate data partition. Computation can often be viewed as a sequence of transformation from the input to output data. In these cases, it is often beneficial to use one of the intermediate stage. Sometimes we use the intermediate stage, because that intermediate stage can be used by other stage. So this can also be happen like this. Let us revisit the example of dense matrix multiplication. We first show how can visualize this computation in terms of intermediate matrices A. For example, if we use this row and multiply with this column B11, B12, so we can get any of the value of matrix T. And for example, we can multiply A12, A22 with the second row, this one, first column, first row, first column, first row, second column, second row. So we can get the answer basically in, it's like C11, C12. This is the resultant matrix. Resultant matrix. This is maybe one of the value of D matrix. So this is basically the intermediate result. That it's not a final result, but the intermediate data. We call intermediate data partition. Like the partial result. The partial result. this row, this column, this row, this column, and the value must be in any of the, not all, any of the matrix member. Okay, not all. Maybe D11, maybe D12. It depends. But the result matrix is same thing here. Like here, this is like same thing. Multiply C11. We have A matrix. We have B matrix. Result matrix is C. We are doing multiplication. Like any of the value of C11, C12, C21, C22. So this is basically intermediate, in between, not full. Now you can see here, a decomposition of intermediate data structure leads the following decomposition into 8 plus 4 tasks. For example, we have 8 plus 4, 12. 8 plus 4, we have 12. How? We have, like, for example, here we have stage 1, and then we have a stage 2. In stage 1, we have A matrix and B matrix. What we have to do, we have to multiply this matrix, and then the result will be here in D, because we have how many values? It should be 8 values. 1, 2, 3, 4, 5, 6, 7, 8 values. And here we can multiply in such a way that this D and plus, this is multiplication and this is addition actually. This is stage 1 is multiplication. Stage 2 is the addition of the matrix. So for example, we get the value here 8, and then with the addition we get the value 4. So how we can do this task into 8 plus 4? This is the example that we are mixing two different matrices. One is multiplication and other is, the second stage basically is addition. In first stage we have multiplication. In second stage, see, we have same D11, D112, same thing, but we have addition, not multiplication. So we get the 4 values here. And with the multiplication, we get the 8 values. So 8 plus 4, 12. Okay. If you want to see this next example, very simple here. See, this is basically the task dependency graph of the decomposition shown in previous slide into 12 like this. 1, 2, 3, 4, 5, 6, 7, 8. This 1, 2 will be in 9, 3, 4 is 10, 5, 6 is 11, and 7, 8 is 12. First we get the 8 result, and then we get the 4 result. The 4 is basically the addition. Like this. Here 8 and plus 2, 4. This 8 here, and this 4 is matrix C. This is matrix C. First is multiplication, and second is the addition. Very simple. Yes. Okay, so this is the slide basically we have to complete by this week. Already finished. Now we have a other decomposition, which is exploratory decomposition. Now we have only 10 slides, not more than only 7, 8 slides. So we will start from this by next week. Exploratory decomposition. Very simple, very easy. we have to use 15 puzzle problem. Then same thing, this puzzle problem here, and then last we have a speculative, and then hybrid. Finish. So only 5-7 slides left. So we have to start in next week. Any question? I don't want to go further.
No question, Doctor.
So if you see this exploratory decomposition, it's used to decompose problem whose underlying computations correspond to search of a space of solution. Search space. How? In this decomposition, we partition the search space into smaller parts. Then search each one of these parts concurrently until the desired solution are found. So problems in this class include a variety of discrete optimization problem, input-output integer programming or QAP, their theorem providing game playing. How? See this one. This is basically the application is 15 puzzle problem. 15 puzzle problem. How? To determine any sequence or a shortest sequence of moves that transform the initial configuration to the final configuration. A is the initial configuration and D is the final. So description is the initial and the final configuration is given. The puzzle can be moved either up, down, left, right. So we have 1, 2, 3, 4, 5, 6. So what we move, we can move this 7 into up. Okay, 7 should be in up. Okay, and then we have 11. 11 must be left side because we only one 11 will be on left. 10 plus 2, 12 will be up. So we solved this problem very easily. We call 15 example 3 moves from initial A to final D. So now we solve this because we have now sorted numbers. Faham, very simple. We call exploratory decomposition. Very simple. We have only 3 moves. 7 will be up, 11 will be left side, and 12 will be up. So we sort out. Only 3 move. Understand?
Yes.
Yeah. So problem solved. The problem can be solved using tree search, also known as state space graph. Step 1, starting the initial configuration, all possible successor configurations are generated. Then each new configuration becomes an independent task of finding the final configuration. And step 3, repeat until the first solution is found. Okay, who will explain this? Very simple. Who will explain this? T4 found the solution first. T4, where is T4? Task 4 here. Yes. Which one will found the solution first? If you move, you can move all, but task 4 will found the solution first. How? You can see here in task 4, we have 11 here. So what we move? We move this 11 to where? Yes.
Right.
Right. Then good. And then yes, in next step. Okay, you are right. Then yes, we move 8 to up. 8 up. If we move 8 up and then we move to 12 up. So we get the sorted numbers. Understand? Very simple. First, we move this. Sorry, in first task, what we have done here? Yes, we move 11 to right, and then we move 8 to up, and then 12 to up, 12 also up. So we sort. If we sort this one, this one, this one, so with this move, only three move, task 4 basically found the solution first. Other may not. Faham? Understand? Yes, because task T4, if you go for T4, how it's found the solution first? Very within three move. Other, no. Other, you can see here, no solution, no solution. Task 3, still no sorted the number. Here, task 2, no sorted. Here, task 4, sorted. Faham? The same thing. Okay. After this, like we have a speculative decomposition in some application, dependencies between tasks are not known. Such application it is impossible to identify independent tasks. There are generally two approaches: conservative approach and optimistic approach. In conservative approach, identify independent tasks only when they are guaranteed they have no dependencies. And optimistic, we have to schedule tasks even when they may potentially be errors. So conservative approach may give little concurrency, little parallelism, and optimistic approach may require rollback mechanism in case of error. Rollback means again start, again start, again start, rollback. So if you see the speculative stage here, for example, another example is the simulation of network of nodes. For instance, an assembly line or a computer network through which packet is passed. Because in a network, the packet is passing like this, packet traverse like this, like router A to B, A to C, A to D, like this. So the task is to simulate the behavior of this network for various input and node delay parameters. Note that network will become unstable for certain values of service rate, queue size. So for example, we have packet A, we have packet B. This is the input, and in between we have routers, we have devices. So this A can be routed from C to direct I, and then D to G or I. It depends. If there is a congestion on C side, so packet must be route from D, G, I. It means that the shortest path, we have to choose the shortest path, but it must be like, for example, uh, delay is a parameter that we have to consider. If, for example, we have two different routes, highway and normal route. If highway is like congested, so we can choose the normal route. Okay, so even normal route is maybe 5 kilometer, highway is 2 kilometer, because highway is already blocked. So we can go to A, D, G, I like this. This is basically called speculative decomposition. Because it learns the behavior of the network or the system. Behavior of the network system is if there is some delay, so we can choose the alternate route. alternate route. So what's the difference? In speculative, the input at branch leading to multiple parallel tasks is unknown. In exploratory, the output of the multiple tasks originating at branch is unknown. We don't know where is the congestion, how long it will take. So we have to see the service rate, the queue size, the delay, everything, and then we can predict which route is best. Last slide is hyper decomposition. We can choose mix. Often a mixed decomposition technique is necessary for decomposing a problem. Consider the following examples. In quicksort, recursive decomposition alone limits concurrency due to dependencies among tasks, uneven size of tasks, uneven size of task. Here, see, left side is 2 tasks, right side is 5 tasks. It different, depends. Uneven task. See here, uneven side. Left side 4, right side 9, like this. We call uneven, not balanced. So uneven task. A mix of data and recursive decomposition is more desirable. In discrete event simulation, there might be concurrency in task processing. A mix of speculative decomposition and data decomposition may work well, even for a simple problem like finding a minimum number of lists. A mix of data and recursive decomposition works well. For example, here, see, the minimum is 2, and here we can find uh, any of the value. Here minimum is, for example, 1, and then we can get any of the number like this. So here 2, here 1, and we can get the 1. Okay, these two, the minimum value is 2, and the 2 set of number 7, 10, 6, 13, 1, 19, 3, 9, the minimum is 1. So 2 and 1, 1 is minimum. Like this, we can do like hybrid techniques. We add additional recursive decomposition as well. So we combine two different decomposition, data and recursive. So we get quick response. So that's all about this. So finish. So your test one will be from this lecture. So this is our test one scheme. So from this week, we'll start our programming part. So hopefully tomorrow inshallah we'll start programming. Okay, so tomorrow there is no tutorial. Tomorrow we'll start the programming. I will tell you the software to download, and then Pastu you have to do some configuration, these kind of things. It will take time, but you should spare in the lab. Okay. Okay, thank you very much. I don't want to linger on.
You are there.
Okay, thank you very much.
Thank you,
Assalamualaikum
Dr.
warahmatullahi wabarakatuh.
Assalamualaikum.
Thank you, Doctor.